Today's lecture is on deductive arguments and propositional logic, focusing on formal aspects of the logic and how to think about these arguments. Here's a sort of roadmap for what we're going to be covering in this lecture. We're going to start with the logical operators and how to translate sentences of English into logical form. We're going to talk about compound statements. Then we're going to talk about truth functions, the truth functions of the logical connectives. Then I'm going to show you how to make truth tables for sentences in logic. And then finally, we're going to talk about how to make truth tables for arguments. The ultimate goal or sort of purpose for learning how the logic of these simple deductive arguments works is so that you can become good at spotting whether or not an argument is valid or invalid kind of immediately. It's also really helpful in this case for you to learn how to formulate a valid argument so that you can avoid in your own writing formulating invalid arguments. And hopefully by the end of this lesson, you'll have the tools to take any argument, formalize it into a simple sentence form, and determine whether or not it's invalid using the method of truth tables. Recapping what we talked a little bit about last week, we can take simple sentences, that is sentences that are of a subject-predicate structure, and we can symbolize these sentences using things that we'll call sentence letters. So simple predicate, subject-predicate sentences are things like Germany is part of Europe, right? Where what we've got here is Germany is the subject and being a part of Europe is the predicate. Really simple. Dogs like to bark. That tree grows apples. Kyle is the instructor of Phil 126. These are all simple sentences, subject-predicate structure, and we can symbolize these sentences using sentence letters, any capital letter A through Z. The only thing to be clear about, right, is that simple sentences do not have any logical connectives as their parts. Compound sentences, on the other hand, are not simple, right? So some sentences really ultimately aren't so simple. They are compound, meaning that they involve some kind of structure, some kind of combinatorial structure, something that combines simple sentences in special ways. And these, the way that these things get combined basically gives these sentences a special logical structure, a specific logical structure. And in this sort of lecture and for part of this class, we will be trying to illuminate that structure, help you to recognize different structures of different kinds of arguments and be able to see right away that certain kinds of arguments are valid or invalid. So for example, here's a compound sentence. Kyle teaches at Cal Poly and at Santa Barbara City College. Another sentence. Either Cameron wants to go to the beach or climb the mountain today. Kamala Harris is vice president only if Joe Biden is president. And Joey is not happy. Now, each of these sentences is logically complex in some way. None of them are of the simple subject-predicate form because each of them contains at least one logical symbol or logical word. Now, when we have logically complex sentences, we can pull out the logical operators first, and then we can translate the leftover sentences using sentence letters, right? So take, for example, the sentence, Joey is not happy. Well, we can pull the negation, the negative, the word not, out of that sentence and turn it into a symbol, right? So there I've got the little tilde, which is our symbol for negation. And basically what this says now is it's not the case that Joey is happy. Similarly, with Kyle teaches at Cal Poly and Santa Barbara City College, we can pull those two sentences out and use the conjunction symbol, the ampersand, to end up with Kyle teaches at Cal Poly and Kyle teaches at SBCC. Finally, with Kamala Harris is vice president only if Joe Biden is president, right? We can pull those two sentences out. We can take Kamala Harris as president as one, or as vice president as one sentence, and Joe Biden as president as another sentence, and translate the phrase only if into our little arrow. And here again is a recap of the logical operators that we'll be using in this class to discuss this section. So we've got negation, conjunction, disjunction, and conditional. For negation, we're using the tilde, which is the little squiggly line. And the way that the tilde works is it attaches to the front of a sentence letter. So if you have a sentence letter, say F, that stands for some sentence, you want to negate that sentence, then you put the tilde in front of F, right? So if F says, say, is that Felix is a cat, then tilde F basically stands for the sentence, it's not the case that Felix is a cat. Conjunction, right, is and. We use the ampersand. And for conjunction, we put sentence letters on either side of the ampersand. Disjunction, we use the wedge, the little letter V. And again, we put sentence letters on either side of the wedge. So we end up with things like G or H there. And then conditional sentences basically are sentences of the form if something, then something else, right? So like if Felix is a cat, then Felix is a mammal. Similarly, sentences with the phrase only if in the middle of them, right? So Kamala Harris is vice president only if Joe Biden is president, right? Those are the kinds of sentences that are of interest here and can be symbolized using the arrow. So here, of course, again, the arrow goes in between two different sentence letters. Just one side note, lots of logical texts use different operating symbols for these logical operators. The most common ones is like for conjunction, sometimes people use a dot, and sometimes for conditional, people use what's called a horseshoe, or something that looks a little bit more like an arrow. But for our class, we're going to be using these symbols because they're really easy to type in on a standard keyboard. There's also another logical symbol that is often discussed, and I think it's discussed in the text that we are reading for this week, called the biconditional. And while the biconditional is logically interesting and relevant, it's unnecessary for us to learn about at the moment. And basically the biconditional is just two different conditionals. It can kind of sort of be understood that way. One going one way and the other going the other way. So it's like, imagine an arrow that is double-sided, right, going both directions. But that's neither here nor there. And you can safely, for the most part, ignore stuff about the biconditional in the reading for this week. All right, so now with the logical operators in hand and simple sentences that we can translate into sentence letters, we can translate compound sentences that have complex logical form. To do this, we're going to construct what's called a translation scheme or a scheme of abbreviation, which is sort of like a map or a key to a map that explains what sentence letters stand for what sentences. So first off, right, we're going to take this scheme of abbreviation. We're going to take the sentence Kamala Harris is vice president and symbolize that with the letter K, and the sentence Joe Biden is president and symbolize that with the letter J. So now the sentence of interest that we're interested in translating into complex logical form. If Kamala Harris is vice president, then Joe Biden is president. Rather simple, straightforward conditional sentence. And using both sort of, okay, so now we've got our logical symbol that stands for if then, and we've got Kamala Harris as vice president on the left and Joe Biden as president on the right. And so we put K arrow J, and that stands for the sentence of interest. And that's ultimately our translation of that sentence. Now we can take the case of negation. So we're going to go through each of the logical operators. So negation is a really simple logical operator, right? It translates phrases like the phrase not, found oftentimes in the middle of a sentence, or the phrase it is not the case that, which is often found at the beginning of a sentence. These different kinds of phrases can be translated into our logical symbol, the tilde. And here's a few examples, right? So Joey is not happy can be translated as not H. It is not the case that Donald Trump is president can be translated as not T. And here's an interesting one. So it is not the case that Kyle does not like teaching logic is can be translated as not L. That's an interesting case because basically what's going on here is we've got a double negative. In this statement, it starts off with it's not the case that, and then follows with Kyle does not like teaching logic. So it's not the case that he does not like teaching logic. Well, that would be not. So now we have two negations, and basically these two negations can be stacked like this. You could have three negations, you could have four negations, right? But basically the sentence letter L here is going to be Kyle does like teaching logic, and then not, right, is how this sentence would be translated. Here we can take the case of conjunction. Conjunction translates the phrases both and the word but. Now, the word but in the middle of a sentence, more often than not, means something other than and, but the way that the word but functions logically basically means the same thing, or it has the same logical function as the word and. And if you're not totally convinced by that, you can sort of check. Whenever the word but is used in a sentence, you can sort of see that both parts of the sentence must be true for the entire sentence to be true. So just take it, I guess, as on my word at this point that the word but gets translated as an ampersand. And we won't run into that too often in thinking about these issues in this class. So the symbol is the ampersand. Examples then, so we've got Cameron loves Joey and John. Here can be translated as C and J, right? Where, the first one is Cameron loves Joey and the second one is Cameron loves John. We've got Joey is hungry but poor, right? Two sentences here, Joey is hungry and Joey is poor, combined with the conjunctive symbol. When you've got a conjunction, each of the sides of the ampersand are called the conjuncts. So there's the left conjunct and the right conjunct. Finally, we've got Donald is angry and not impressed. Well, the two sentences here would be Donald is angry and Donald is impressed. And then that would be symbolized as A, right, for Donald is angry, and ampersand, negation for the not here, impressed, right? So Donald is angry, and it is not the case that Donald is impressed, is what that last sentence says. Disjunction now is what we mean when we're talking about the wedge, and this disjunction is the logical sort of form of the word or, also the word unless. It's a little bit confusing, but it actually works in the same way as or, surprisingly. Again, don't worry too much if that sounds weird to you. You can take my word for it. It's something that's sort of mind-blowing until you really, really think hard about it, and it's difficult to do that on the first pass. So the symbol again is the lowercase v. It's called the wedge. And some examples here, right? So River is either annoyed or tired. Well, that can be translated into River is annoyed and the sentence River is tired. And then you can put the wedge in between those two to get River is annoyed or River is tired. Similarly, right, UFOs are real unless there is a big conspiracy. Well, that actually means the same thing as UFOs are real or there is a big conspiracy. So you can basically just put those on either side of the wedge. UFOs are real or there is a big conspiracy, right, for U or C here. And then finally, right, this sort of works as well. Jesus either rose from the dead or he didn't, right? Well, that's just the same sentence. Jesus rose from the dead. And then one of them has a negation in front of it, right? So if we take the word that Jesus rose from the dead and make the letter R stand for it, then we have R, wedge, not R, right? Negation R. So either Jesus rose from the dead or Jesus didn't rise from the dead. Finally, here we're on to my favorite of the logical operators, the conditional. The conditional is rather confusing and difficult to understand in lots of cases, but we're going to work on it a little bit more in depth. And so here's sort of a first primer of it. So the phrases that conditional phrases are the phrase if then and the phrase only if. The phrase if then, the if is followed by some words, right? A simple sentence. And the then is also followed by a simple sentence. When you find only if in English in sentences, it's usually, there are two simple sentences on either side of it. So we just use this one symbol, the little arrow. Different textbooks, again, use different symbols. Some of them use a horseshoe, which basically looks like a backwards C. Some of them use a more serious arrow. It's just for our easy use to use this little sideways V, this little bracket arrow thing, because it's easier to type, right? And I don't want you all like having to search for weird symbols on the internet and stuff to copy and paste. That's just a pain in the butt. When you have a conditional statement, there are two parts to it. The first part is called the antecedent. That's the if part, the part that goes up front. The if part is the antecedent of the conditional. And then the then part, that's the second part, it's the second half of the conditional, that's called the consequent. So for each conditional, you have the antecedent on the left and the consequent on the right. So now some examples, right? If Joey is hungry, he hasn't eaten enough, right? So now we've got two sentences. Joey is hungry and Joey has eaten enough, right? We'll symbolize that as H and as E. And then we can symbolize that the if-then section, right? So actually, it's even interesting. In this sentence, the then doesn't even show up, but it's ultimately implied, right? If Joey is hungry, then he hasn't eaten enough. But in English, we oftentimes just skip over words that are, they sort of should be there, but they don't show up. So you can sort of see that and take it for what it is. But this is the proper way of translating a sentence like this. If Joey is hungry, then he hasn't eaten enough is H arrow negation E, where negation, right, goes for the not. It's not the case that he's eaten enough. More simple one, right? Kamala is vice president only if Joe Biden is president. That one's super obvious and straightforward. You just translate the only if as an arrow and stick it right there in between the K and the J. And then finally, right, if Felix is a cat, then Felix is a mammal, right? So Felix is a cat is the letter C, and Felix is a mammal is the letter M, and the arrow goes right in between as well. All right. Now that we know how to translate some simple sentences and some logically kind of more complex ones with one operator, we can begin to translate sentences with more than one operator. So take this example sentence. If Joe is not president and Kamala is not vice president, then either Donald Trump is president or the United States has been destroyed, right? Well, now we can, symbolize each of those sentences, right? So what we would do is we'll take Joe is president as J. We'll take Kamala is vice president as K. Then we'll take Donald is president as D. And we'll take the United States has been destroyed as U. Great. Well, now we're going to string those together and put all of the logical connectives in there, right? So the first part of the sentence says is if, right? So we've got this big if-then sentence here. So that is we need to basically like in between the if, basically where the then part comes in. That's usually where the arrow is going to go. So we can kind of see that the then part is going to be in the middle. So let's just wait on that. The Joe is not president, right? Okay, well, we've got a negation there for not. Well, we need to put that in front of the J. So we've got not J, and Kamala is not vice president. Okay, well, again, we've got a negation there. So we've got not J and not K. Then we've got our then. So let's put our arrow in right after those two. And then we've got the sentence, Donald is president or the United States has been destroyed. Okay, so let's put D there, or and then the wedge for the or, and the letter U. Now, this is good so far, except for the fact that ultimately this long sentence is confusing because you don't actually know how to read it. And the reason you don't know how to read it is because all of these conjunctions, or all of these logical operators that are in the sentence, like it doesn't tell you which ones matter, which ones take what's called scope over the other ones. And you don't know which connective is what we call the main connective in this sentence. Now, in the example sentence, the main connective is the conditional, right? Because ultimately the whole sentence is a conditional form. It says, if Joe isn't president and Kamala isn't president, then either Donald Trump is president or the United States has been destroyed, right? And that's pretty obvious from the context of the sentence, like the way that the sentence itself is set up, but it's not obvious when it comes to the symbolization. When we've symbolized the sentence, it becomes less obvious what sort of part of the sentence takes precedent over the others. So we introduce parentheses in the same way that you do in sort of math to kind of make it clearer which part of the sentences like go together and which part of the sentence sort of is the biggest part, which part takes the most is the most important, right? So in this case, because not J and not K go together, right? Joe is not president and Kamala is not vice president. We are going to put parentheses around those two, and then also D or U, right? That's the second half of the statement, the whole sentence, and so we're going to put parentheses around those. Now, we use these parentheses to capture what's called the scope of logical operators. So just like in math, right, when you have to use parentheses in order to sort of know what to do first, right? It's the, what is it called? PEMDAS. Parentheses tells you what to do first, right? So in this math equation, right, 5 minus 3 divided by 6 plus 9, you would do the division first if it weren't for the parentheses, right? And that would be, it would make things much more complicated in certain ways. Instead, what you do here is you do the 5 minus 3 first, and then you do the 6 plus 9, and then you'd have, 2 over 15, right? The parentheses tell you what to treat together first and what to treat later. And this is going to matter when we get to the rules, to truth tables. But for now, ultimately, it's helpful to just have more examples. So take this example, this statement: if UFOs are real, then the government is involved in a cover-up, or aliens are really good at hiding, or we are living in a simulation created by aliens, right? So now, taking this long sentence, we can turn it into each of the sections into a sentence letter using the scheme of abbreviation, right? So we've got U for UFOs are real, G for the government is involved in a cover-up, A for aliens are good at hiding, and S for we live in a simulation. And then we can sort of see how all of this is going to go, right? So the sentence, the way that the sentence is set up, the original sentence, it says, if UFOs are real, then, right? And then the whole rest of it, right, is basically just a bunch of disjunctions. It's like, well, either UFOs are real, or, right, okay, if UFOs are real, then, like, the government is involved in a cover-up, or aliens are really good at hiding, or we are living in a simulation created by aliens. So it's like this whole second half of the statement is just a bunch of different options. So we know, given the way that the sentence is structured, that the conditional is the sort of main operator in the sentence. But we still need to sort of pair off some of the other parts of the sentence, right? So what's going to happen here is, well, okay, we're going to take U as the antecedent of the conditional and then put the arrow right after it. And then we need to sort of group these disjunctions. And the disjunctions are sort of more naturally grouped in this way, right? Either the government is involved in a cover-up or the aliens are really good at hiding. Or there's this whole other option that it could just be that we're all living in a simulation that was created by the aliens, right? And so this is kind of maybe the most natural way of grouping each of these sentences in such a way as to make clear how we want this sentence to be read and ultimately translated. Here's another example. Kyle doesn't like vanilla ice cream. Either Kyle likes vanilla ice cream or doesn't like vanilla ice cream, or well, let's just see, right? So here we've got a scheme of abbreviation. The letter I stands for Kyle likes vanilla ice cream. And so really simple symbolization, right? Kyle doesn't like vanilla ice cream, just comes out as not I. Well, now something a little bit more complicated. Either Kyle likes vanilla ice cream or he doesn't like vanilla ice cream, only if he likes chocolate ice cream and strawberry ice cream. Now, this is a little bit more complex, but you can kind of oftentimes get a little hint here. The main operator of a sentence is, in lots of cases, sometimes comes where the comma is, but it's not always clear. In this case, though, it looks like, so it's one of these weird situations where the sort of way that you read the sentence tells you how you should order the different symbols, right? So either Kyle likes vanilla ice cream or he doesn't like vanilla ice cream only if he likes chocolate ice cream and strawberry ice cream. Well, that's it's a strange sentence that's kind of convoluted to begin with. So it's not, you don't have to worry a whole lot about it. But what's going on here? So we've got either Kyle likes vanilla ice cream, I, and then the wedge, or, and then we've got this rather complex thing, right? If he doesn't like vanilla ice cream, right? He doesn't like vanilla ice cream only if he likes chocolate ice cream and strawberry ice cream. So then we've got not I, arrow, C and S, right? So he doesn't like vanilla ice cream only if he likes chocolate and vanilla and strawberry. All right, and then finally the third statement here. It's not the case that if Kyle likes chocolate ice cream, then if he doesn't like vanilla ice cream, then he does like chocolate ice cream. Now this is just a big messy sentence, but it's to sort of help you see how best to symbolize these things. So here again, we've got the scheme of abbreviation. Here we're just using the letter C and the letter I. But as you can sort of see, what comes out in front of the sentence is this phrase, it's not the case that. Now, this is not used as often as in normal English, but sometimes. And in logic, we use this statement a lot just because of the negation sign. So it's not the case that, well, that should give you a big red flag. Oh, okay, this whole sentence is going to be negated. So we can know right off the bat that we should stick a negation in front of the entire sentence. Now, normally negations go just in front of sentence letters. But sometimes when you've got an entire complex thing that's being negated, then the negation goes outside of the parentheses. So here we've got negation outside of the parentheses, and it says if it's not the case that. No, and then it says if Kyle likes chocolate ice cream. Okay, so now we know we've got a conditional where the antecedent, the left side of the conditional, is the sentence Kyle likes chocolate ice cream. So that's letter C. Then we put the arrow in, right, because the then comes. And from there, we've got a whole nother conditional that pops right up, right? So if Kyle likes chocolate ice cream, then if he doesn't like vanilla ice cream, right? Oh, wow, okay, so now we've got a new conditional coming in. And that conditional seems a little bit more self-contained, right? So we need to put the parentheses in, a new parenthesis in, just to sort of keep this separated off. So if he doesn't like vanilla ice cream, then he does like chocolate ice cream. Okay, well then this is another conditional. So it's if it's not the case that I, then C. And as you can sort of see here, like where each of these logical symbols kind of gets subbed in and where each of these sentence letters gets subbed in for the sentence as it stands. All right, now that you've gotten a little primer on how to translate these sentences, the next thing to do is to learn the truth functions for each of these logical symbols. Now, what exactly is going on when it comes to thinking about truth functions? Well, remember back to week 2 when we talked about the law of excluded middle. The law of excluded middle says that for every property that something that can be had by something, everything in the world either has that property or it doesn't have that property. Well, when we think about the notion of truth, we can apply that property to sentences. And we can see that every sentence either has got to be true or not true, right? According to the law of excluded middle. So if all sentences are either true or not true, well, and ultimately then we can just call being not true the same as being false. Well, then we can understand sentences and think of sentence letters as having values, right? Where the values are, well, the sentence is either true or it's false. And then using this information, right, if we know that a sentence is true or a sentence is false, then we can sort of compute or calculate the truth value of a more logically complex sentence, right? It's kind of similar to thinking about like you doing math where you've got variables, and the variable like x or y, you don't really know what the number is, right? But once you do know the number that the variable stands for, then you can all of a sudden do the computation, right? You can all of a sudden do the calculation. Well, the same thing is going to go here, right? So take this complex sentence. So it's C arrow B ampersand G. Well, what's that say? It says if C, then B and G. Now, if we've got that statement, and that doesn't, we don't know if this sentence as it stands is true yet or false. But if we have the truth values of each of the individual sentences, right, C, B, and G, then we'll ultimately be able to calculate the truth value of the entire sentence as it stands. And so what I've got here is just a little diagram, right? If we assume that the sentence letter C is true, that the sentence B is false, and that the sentence G is false, well, then this is what's going to happen, right? C is true, B and G are both false. Well, if B and G are both false, right, we start off inside the parentheses. Well, if B and G are both false, well, a conjunction where we've got two false sentences is also going to be false. We'll talk about this in a moment. And then in this case where C is true, but both B and G are false, then the way that the truth value, the truth condition, the truth function ultimately of the conditional statement here is also going to be false. If that went over your head, that's fine. We're about to jump right into it. All right, so truth functions basically work like this. Each connective has its own truth function. So this is just like the basic symbols that you have in math, right? You're learning a new symbol, a new way to manipulate symbols, a new way to think about these things, a new function. So just like plus, right? So plus has this function where if you add two numbers, right? If you put two numbers on each side of plus, then you end up with a resulting value, right? So you put the number 2 on the left side and the number 3 on the right side of the plus sign. Well, what's the ultimate, what's the value that you end up with? Well, you end up with 5, right? Now, the same thing goes with sentence letters and the logical operator symbols that we're using, and truth values. And the easiest one here is negation. Now, what exactly is going on in this little diagram? Well, on the left, we just have the sentence letter A, right? And the sentence letter A could be either true or false. So in the first column, that's the up and down, we have A, and then right below A, we have true and then false. So those are those two rows, right? The first row is and what we can think of is we can think of each row as a different scenario, like a different possible way that the world could be. So, take take the sentence A. Let's say that the sentence A stands for the sentence in English that it's raining. Well, in some scenarios, A is true, right? And in some scenarios, A is false. And now what we want to do here, and the way that we're thinking about this is, well, okay, we want to take all of the possible situations that A could be in, right? Like it could be a situation in which it's raining, and it could be a situation in which it's not raining. Great. So we're just trying to diagram all of the possible situations here. And then now we move next to A, and we have the symbol not A, right? Tilde A, which just means the negation of A. Now, what does that statement say? Well, if the sentence A basically just says it's raining, then the sentence not A basically just says it's not raining. And now we can sort of begin to see, right? Well, in the situation in which A is true, well, not A is going to be false, right? If it is raining, then it's not the case that it's not raining. And similarly in the opposite case, right? If it's not raining, then it's true that it's not raining, right? If A is false, then not A is going to be true. And in this case, basically what I've just kind of been going over is this is the really simplest case of a truth function. So what's going on here is when you add the negation to a sentence, well, if that sentence is true, then the thing that sort of pops out, right, the resultant truth value is going to be false. And if the sentence is false, well, then the resultant sentence is going to be true. So that's sort of the straightforward way of trying to understand what's going on with negation. Whenever you have a negated sentence, you simply flip the truth value from one side to the other. Now take the case of conjunction. The truth function for conjunction is pretty straightforward. Any statement that is a conjunction, right, A and B here, is going to be true only in cases in which both A is true and B is true, right? I mean, that's basically just saying A and B. But we want to do the same thing that we did previously. So basically what's going on here is on in the left two columns, the column under A and the column under B, we have all of the possible scenarios that the world could be in, regardless of what the letters A and B mean, right? Regardless of what sentences A stands for and what sentence B stands for. Right, there's going to be one scenario in which the sentence A is true and the sentence B is true. That's row 1. There's going to be one situation in the world in which sentence A is true and sentence B is false. That's row 2. There's going to be one possible situation in the world in which A is false and B is true. That's row 3. And finally, there's a situation in which both A is true, or A is false and B is false, right? That's row 4. Basically, so now what we have here is all of the possible situations that the world could be in with respect to the truth values of sentence letter A and sentence letter B. And now we can compute the resultant truth function for sentence of the form A and B, right? Sentence of the form A and B is going to be true just in cases where the sentence A is true and the sentence B is true. And it's going to be false in all the other situations, right? So on line 2, row 2 here, right, B is false, and so the sentence is false. On row 3, A is false, and so the sentence is false. And finally, on row 4, they're both false. Just a hint also for the way that you set up truth tables. On the left-hand side of a truth table, you always kind of go, you do half true and then half false kind of to start, and then you move down, and sort of the last part of the truth table is going to be alternating, and we'll go over that again momentarily. All right, the truth function for disjunction, or the word or, is true just in case one of the disjuncts are true, right? And in a disjunctive sentence, a sentence with the wedge in it, each of the sides are called the disjuncts, right? So the left side is the left disjunct and the right side is the right disjunct. And once again, just going through this again, here in the table, we have all of the possible truth value pairings, right? Under the different possible scenarios that the world might be in. Right? It could be that A is true and B is true. It could be that A is true and B is false. It could be that A is false and B is true. Or it could be that A is false and B is false. Those are all the possible scenarios regarding the truth value of these sentences, right? And so now we can compute the truth function of the sentence A or B. And the way that that works is basically like this, right? In a sentence, like take any sentence that's an or sentence, right? So, and just think about it. If you've got an or then only one part of the sentence really has to be true for the entire sentence to be true, right? Like take this really crazy sentence, right? Pigs can fly or Donald Trump is, or no, like pigs can fly or Joe Biden is president. Great, okay, that's going to be true. It's a weird sentence, but it's true because Joe Biden is president. So here, that's how it goes here, right? Anytime one of the disjuncts is true, then the entire disjunction is true, right? The only time in which the disjunction is false is when both of the disjuncts are false. Finally, we have the truth function of the conditional. And the conditional is a little bit more tricky, and you got to pay a little bit more attention to the actual truth function here. A conditional statement is true just in case either the antecedent is false or the consequent is true. And remember, the antecedent is the first half of the conditional, the left-hand side, and the consequent is the right-hand side, the second half of the conditional. Another way of thinking about it is the antecedent is the if part and the consequent is the then part. And the only case in a conditional statement in which the statement will turn out to be false is going to be the case in which the antecedent is true, that's the first part, and the consequent is false, that's the second part. Now this is a little bit confusing because sometimes the antecedent is false, and ultimately that will make weird statements turn out to be true. This is what's called trivial truth. But you don't have to worry too much about that at the moment. We'll talk about that another time. At this point, just trust me that this is how the truth function for what is called the material conditional works. And the conditional statements that we're going to be focusing on are just this form of conditional. Here is a helpful list of all of the truth functions that we will be using in this class. All right, now that we know all of the truth functions of the different connectives, we can compute the truth tables for all kinds of translated logical sentences. Now, the way that this is going to work is through this multi-step process. Take any well-formed logical sentence and place it in the last column of a truth table. Then put each of the simple sentences from that logical sentence to the left of the logical sentence, sort of by themselves. The number of sentence letters that is in the sentence that you're interested in, the well-formed sentence, is going to determine how many rows the truth table is going to need. And the formula here is 2 to the n rows, where n equals the number of sentence letters, right? So if there's only 2 sentence letters in the sentence that you're concerned with, then you're going to need 4 rows in the truth table. If there's 3 sentence letters, you'll need 8 rows. If there's 4 sentence letters, you'll need 16 rows. And it goes up. We're going to try and stick to 3 sentence letters at the most, because anything beyond that just starts to get out of hand. So now for each sentence letter, what you're going to do is assign truth or falsehood to it on each sort of row, so that every possible scenario has been accounted for. And the trick here is to start from the left and assign, depending on how many rows you have, half T's and then half F's, and then move one over and do, a quarter T, a quarter F, a quarter T, a quarter F, and then move one over again and do the same, further down until you get to the final row where you just have T's and F's alternating, right? One T, then one F, then one T, then one F. If we're sticking to 3 sentences in this case, then you'll never have more than 8 rows. And so basically what'll happen is on the left-hand row, you'll have 4 T's, 4 F's, then you'll have two T's, two F's, two T's, two F's, right? And then on the final one, you'll have TF, 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 TF all the way down. Finally, using the table now that you've partially filled out, you can compute the original logical sentence by translating over all the relevant T's and F's, and then using the truth functions that you now know to determine what the ultimate, what ultimately the sentence, what the sentence's truth value ultimately is. So here is a really simple example. Take the sentence, it's not the case that A or B. Well, what are we going to do now? Well, okay, that's just two sentence letters, A and B. So we're going to make a really simple table here with 4 rows. And we put A down and then we put B down. And under A, we're going to write out T 2 times and then F 2 times. And under B, we're going to do alternating TF, TF. All right, now knowing that, we can translate over the trues and falses to our sentence that we're interested in, our example sentence. And we can see that example sentence is complicated. Now, where we're going to start is inside the parentheses. Just like in math, you always start inside the parentheses to try and figure out what you should be doing first. And so first we need to figure out the truth value of the sentence A or B. And if you go back and check the truth function for what's called disjunction, right? The sentence A or B is going to be true just in case A is true or B is true, right? Just in case one of the disjuncts is true. Well, now looking at our table here, A is true or B is true in the first 3 rows. And only on the 4th row is A false and B false. So we can just sort of write that down on our final column here, right? So A or B is true in the first one, A or B is true in the second, A or B is true in the third, and A or B is false in the final one. And then now we know that we have to like the sort of next step is to do the truth function using negation. And so now we know in each of these scenarios where A or B is true, if we're going to negate it, we're just going to flip the truth value, right? So where in the first row A or B is true, so not A or B is false. Same in the second row, same in the third row, and then finally in the 4th row where A or B is false, we know that not A or B is true. And that's basically it. That's how you calculate the truth values, the possible truth values for this sentence. It's not the case that A or B. Now let's try a more complicated example. So here what we've got, first let me read the sentence for you. The sentence that we're trying to compute is if it's not the case that K, then N or M and N. Now how are we going to compute this sentence? Well, the first thing that we do is we write out the letter K, the letter M, and the letter N on the left-hand side of the truth table, and then our sentence that we want to compute on the right-hand side here. And then we need to write out every possible truth table combination, every possible combination of truth values that the sentence letters could possibly have. And the way to do that, again, is to start on the left and do half T's and half F's, and then go to the middle and do 2 T's, 2 F's, 2 T's, and 2 F's. And then finally, for N here, sort of on the right of these 3, we go alternating TF, 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 TF. Now, given that setup, that's the beginning, that's just the beginning of this, we now have on each row all of the possibilities of truth and falsity for these sentences, right? We have every possible scenario. We have the scenario in which K, M, and N are all true. We have the scenario in which they're all false. We have the scenario in which, K is true, M is false, and N is false. We have we have all of those possible scenarios covered. And so now we can, basically figure out whether or not the final sentence is going to be true or false depending on any of the scenarios given so far. So now the first thing that we want to do is start on the inside of the parentheses, right? To start on the inside of the parentheses, we need to go look at these little, the sort of different sentences, and then we can compute those. And then from there, we can compute the more complicated ones, right? We can sort of work our way out. So the M and N is the innermost parenthesis, sentence, basically complex sentence. And now what we can do is we can take that and using our truth functions, the table that we had earlier, we can figure it out. So the sentence M and N is going to be true only in cases in which both M is true and N is true. So knowing the function of the conjunction, well, in line 1, both M and N are true, so true. In line 2, M is true, but N is false, so that's false, right? And then it keeps going until line, 5, where both M and N are true again, and then it's false the rest of the way down as well. All right, great. Now we've computed the truth function for that innermost section of the sentence. But that's, but now we're going to have to use that to try and compute the next level up. So now using the truth values that we just computed of M and N, we can try to compute the truth values of the wedge of disjunction using that, right? So what exactly is going on here? Well, now we've got N or M and N, right? And because we now know the truth values of M and N, we can just compare N and M and N, and then we can figure out the truth values here, right? So because it's a disjunction, we know that the truth function that we need to follow is disjunction is true just in case one of the disjuncts is true. So that means anytime either N or M and N are true, then the whole sentence is going to be true. And so we can just kind of go right down the line there, right? So, in the first one, both sides are true, so the sentence is true. In the second one, both sides are false, so the sentence is false. On the third line, N is true, and so the disjunction is true. And so on down the line, right? Filling out, okay, so it's TF, 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 TF. Basically, it's just the same as N in this case. So now we've got this disjunction determined. We've got the truth value of the disjunction. So we now know the truth value of the sentence, N or M and N. Okay, great. Well, now using this, we can go a step bigger even. But first, we should take into account the fact that the largest scope of the entire sentence is the largest scope is the conditional. We need to also recognize that the K out in front is negated on its own, right? Because the K itself is negated on its own, we want to basically just flip the truth value of the K on the left to sort of reflect what not K actually means. So not K here translated, once we've done the truth function, we've calculated it out, right? So if K is true, then not K is false. And that's going to go, so that's going to go for the first 4 there. And then if where K is false, then not K is true. And that's going to go for the second 4. So now with both the sort of not K and the N or MN sentences translated, calculated, we now have the truth tables for each of those parts of this complex sentence. We can finally compute the truth table, the truth value assignment of the arrow in this statement, right? We can finally compute that, basically going back, remembering that the truth function of the conditional is such that the resulting statement is true in any case in which the antecedent is false or the consequent is true. That is, any statement in which the first half of the sentence is false or the second half of the sentence is true. And remember, the only case in which a conditional is false is the case in which the antecedent, the first half, is true and the second half, the consequent, is false. So basically what we're looking for here on these two rows are just cases in which the sentence letter, where the left-hand side is true and the right-hand side is false. That's it. And otherwise, we know that the arrow here is going to be true. So now we'll compute these things, right? So the first one, not K, is false, and N or M and N is true. Well, that's we know that that's going to be true because the antecedent is false. Similarly for the next three, right? So rows 2 through 4, the antecedent is false, and remember the truth function for the conditional says that the conditional is true if the antecedent is false or the conditional is true, or the consequent is true. Great. And then so now we're on line 5. 5 is true antecedent and true consequent. Great. Well, that's going to be true because the consequent is true. But finally, oh, look, on line 6, we find a situation in which the antecedent is true. That is, not K is true, but N or M and N is false. So now we have a particular line in which the entire statement is false. Similarly, on the last line, line 8, we have another situation in which the antecedent is true and the consequent is false, making the entire statement false. Now we know that this complex statement is false given a particular truth value assignment. Given the assignment that K is false, M is true, and N is false, then the entire statement is false. Similarly, we know this other truth value assignment where all three of them are false makes this sentence itself false as well. Now, because we know that under some possible situation, this sentence is false, then, but under some other possible situations, this sentence is true. That is, under some truth value assignment to the letters, you get true, and under another truth value assignment to the letters, you get false. Then we know now that this sentence is called a contingent sentence. That is, sometimes it could be true and sometimes it could be false, depending on how the facts actually are. There are some sentences, though, the way that this thing goes, it'll turn out that they're going to always be true. Sentences that turn out to always be true, no matter how the premises are set up, are called necessarily true sentences. Then there will be some other sentences that are always going to be false, and those sentences are called contradictory sentences. Now, once again, truth tables with more than 3 sentence letters can get really long and can be very difficult to deal with. So I'm going to try to avoid them for your sake. But you will need to practice these, and they will be on the midterm and final exam. So check Canvas this week use this week's reading to find example problems for you to try out on your own. All right. Finally, we're on the home stretch for what the purpose of all of this ultimately is. The reason that we've gone through all of this is that once you come to recognize what's going on here, you'll be able to show whether certain arguments are invalid just from using the truth table method. The basic idea here is this. We can take each sentence in an argument and run it through the truth table. And if we run the sentences through the truth table, then we can calculate the truth values for each of the sentences given every possible variation of true and false for each sentence letter. Once we've done that, we can determine if there are any scenarios that is, situations where the T's and F's are thus and so for each sentence letter, we can determine whether or not there are any scenarios, any rows of the truth table, where all of the premises of the argument are true, but the conclusion of the argument is false. And then we know, given our definition of validity, that if there are any such cases, that is, any cases where an argument is set up such that the premises are true and the conclusion is false, then we know that that argument is not valid. It is called an invalid argument. And that's ultimately what we're looking for. We're looking for situations in which it's possible for the premises to be true and yet the conclusion to be false. If we can find any of those, then we know we have an invalid argument. Let's start with a really simple argument. This argument is actually valid. This is a classic style of argument called modus tollens, which we'll be covering soon. But this is basically how you fill out the truth table for an argument. First, you're going to take look at the argument and determine the sentence letters that you need. So we've got not Q, if P then Q, and the conclusion there is not P. Well, okay, that means that we need the sentence letter Q and we need the sentence letter P. So P here on the left, right, we've got true, true, false, false. And then Q here afterwards, we've got true, false, true, false. All right. Well, now we can start looking at the premises, right? The first premise is not Q. Well, computing that truth value is rather simple, right? Not Q, we just flip the truth values of Q, right? So we've got false, true, false, true. Then we can go over to premise 2, which says if P, then Q. And in if P then Q, right, we're going to be computing the truth value using the truth function of the conditional. And the truth function of the conditional, remember, it's always true unless the antecedent, the first part, is true and the consequent, the second part, is false. And as it turns out, the only situation in which P is true and Q is false is line 2. So every other line, right, either P is false or Q is true. So line 2 is the only one that turns out to be false. So we have true, false, true, true. And then finally, the conclusion, not P, we have, we've just basically flipped the truth values from the first line of P. So we just end up with false, false, true, true. Now, basically, once you've finished filling out the truth table here, what you are finally now looking for in order to try and determine whether or not the argument is invalid is to try and see if there's any situation in which the premises are true and the conclusion is false. And this is actually rather easy to do here in this case, because there's only one line in which all of the premises are true. And that line is the last one, right? So the idea here is like you can ignore safely just the P by itself and just the Q by itself, because you're just looking for the premises, right? So the premises here are not Q and if P then Q, and the conclusion is not P. And so now you're looking to see if there are any lines where not Q is true and if P then Q is true. Okay, and that's only the bottom line. And then you're trying to see if not P is false on any lines where the premises are true. And because it's only the bottom line that matters, well, look, it's true. So so in this case, given the way that it's set up, we've given all of the possibilities given for the truth values of P and Q. And given all of the possibilities for the truth values of P and Q, there are no situations in which the premises of the argument are true and the conclusion is false. That's just how it works, and that ultimately helps solidify that this argument is valid, basically just by showing us that it's not an invalid argument. Again, let me reiterate, in this case, there are no rows of the truth table where the premises are true and the conclusion is false. And that's ultimately what makes this a valid argument. Now let's take an example of an invalid argument. So the argument here is, so basically we've just got two premises and a conclusion. The first premise says P or R. The second premise says if not P, then not R. And the conclusion is just R. Now, again, what are we looking for? We're looking for a scenario in which the premises are true and the conclusion is false. If we can find such a scenario, then we can know that we've got an invalid argument. So what are we going to do? Okay, let's set this up, right? So we've got our truth table here where we've just got the letters P and R. So P, so it's just only a four-line truth table. P is true, so we've got true, false, false. R, we've got true, false, Great. Now we can compute premise one. In premise one, we know it's P or R. We go back and look at our truth function, right? The truth function for disjunction, P or R, we know is that if either of the disjuncts is true, then the whole sentence is true. So basically, anytime P is true or R is true in this case, the whole sentence is going to come out true. Well, as that turns out, it's going to be true in every situation except for the final one, right? So that's the only case in which the sentence P or R is false, because both P is false and R is false. Okay, great. Now let's look at premise two. This is a little bit more complicated. Premise two has two negations in it, right? And so we need to figure those out first. Well, luckily that just means flipping the truth value for each one. So for not P, we just flip the truth value for P. So we've got false, false, true, true. And for R, we've got for not R, we've got false, true, false, true. All right, now we can compute the truth function of the conditional in premise two. And remember, the truth function of the conditional is always that, right, a conditional is true just in case the antecedent, the first part, is false, or the consequent, the second part, is true. And the only case in which a conditional is false is when the antecedent is true, the first part, and the consequent is false, the second part. So let's just look down the line here on premise two. In the first row, we've got false, not P is false and not R is false, so that makes the conditional true. In the second line, we've got not P is false and not R is true. Well, that's false, true, not true, false. So the second line, the conditional is also true. Third line, we've got not P is true and not R is false. Great. Well, there's a situation in which the conditional turns out to be false, right? Because the antecedent is true and the consequent is false. And then finally, the fourth line, right, where we've got the antecedent is false and the consequent is true. So not P is false and not R is true. Well, there again, we know the conditional itself is true. Finally, on the conclusion is just R, so we can just copy the true, false from the other line. All right. Now, lastly, the last thing that we're doing here is trying to determine whether or not any line on the truth table gives us a situation in which the premises are true and the conclusion is false. If we can find such a line, then we know that the argument is invalid. And look on line 2. Premise 1 is true, premise 2 is true, and yet the conclusion turns out to be false. So now we know that this argument, the argument P or R, premise 1 P or R, premise 2 if not P then not R, conclusion R, we know that that argument is not a valid argument. What does that mean again? Well, it means that there's situations in which the premises could be true, but the conclusion's not true. And that means that the premises don't guarantee the conclusion. They don't, if the premises are true, it's not guaranteed that the conclusion is going to be true as well. Because of that, we now know that the argument is invalid, and so we can disregard the argument, at least when insofar as we're interested in deductive arguments. Again, just to reiterate, because this is the most important thing, the argument is invalid because there is a row on the truth table where the premises are true but the conclusion is false. All right, now it's time to go and practice and try your hand at doing these truth tables and understanding all of this material. The only way ultimately to understand any of this is to try and do it yourself. You can use the reading for this week to help, and I'm also going to be posting some more videos where I go through how to do certain problems myself. If you get stuck or find any of this extremely difficult, definitely come to office hours where we can walk through it together.